Well, we have been as an MN consultants, it's a long journey. We are doing a lot of projects, we are doing a lot of tall structures throughout the city as well as in Gurgaon. And the demand in the market, what we could see, luxury, 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 and luxury, and ultra luxury. You know, there's no limit to it. And with that luxury apartments and living, people are also trying to get a feel of, in fact, amenities. Their amenities also should be super luxury. And probably that is not attached to the ground, and they are taking it up the air and in the floating concept that has come up. The swimming pools, the jogging track, the performance spaces, a golf course, mini golf course, are all up in the sky. And our architects friend, I could see many of them, brilliant architects, we the poor structural engineers, pushing them us hard. And our back is already at the walls, and we are spending sleepless nights to make them happy, and the client also to make the clients happy. But we are spending sleepless nights, I tell you. But nevertheless, we have tried, and probably we have been successful in many of our endeavor. I don't know where the limit ends, but well, let's see how we can satisfy our architect friends and take the journey up to the I don't know where. Today's topic, as you could see, is it's connecting heights. Tall building structures these days, the roofs are all connected. You have a club there, 4 levels of club there, and these buildings are, these buildings are, some of them are 10 meters apart, some of them are 20 meters apart, some of them are 50 meters apart, and you still need the connection. And with the tall building structures, you are aware that the movement of the buildings are in different modes. One building, because it's separated, one can move in this direction, the other one can move in the other directions. And then the connection has to take care of that, compatible with all these movements. And the twists and turns that happens in this thing is a nightmare that the structural engineer has to carry on. So these connecting heights, I think, in the international scenario, it's all started in Singapore, Marina Bay Sands. And thereon, I think the culture has come up in India in a large way. And one such endeavor, which I think everybody is aware of, that is the atmosphere project that we have in our city, is talk of the town, and probably the talk of the in our country. It's one of the major project, and ultra luxury apartment buildings, and then you have the club and at the top with 4 levels of deck there, and carrying whatnot, or everything, all jogging tracks, and then you have your performance spaces, games room, everything. Now, this, as I say, this is as an luxury condominium. It's a 2 lakh square feet building, and it's connected by, you can see that this is see, this is connecting the 2 building blocks. Where's the connector? Sorry. Anyway, so this is the club that is connecting the 2 buildings, and this is a 4-level deck club building on the top. And the challenge is that how to construct this thing, and it's a, see the shape of the building, the shape of this, this club that we have there. It's more of a club rather than, it's more of a cloud rather than anything else, because it's at the 100 meters height from the ground. So it's almost touching the cloud that the architects imagined, you know. So the shape has been given like this. And you know, may understand this, between these two buildings, the gap is about 50 meters. And interestingly, this club was named as Dea. It's a Bengali term, which means heavenly cloud, and it has been coined by our famous Rabindranath Tagore. In one or two of his songs, you can find this term is called Dea. It's heavenly cloud. So it has been named like that, and we all call this as Dea. What's happening? Next is not coming. Oh, sorry. Okay. Thank you. So a part of this there, as you can see, is a, as I said, it's a floating luxury club, 400 feet above the ground, and it is an inspiration to all of us, and it was conceived long back. I tell you, it's in the year 2010, and we didn't know any clue about how to do the thing, how to design the thing, how to support the whole thing at that height. It was a huge challenge at that time. But eventually, along with our team, it was led by Dr. Hussain Sorabi of Web Structure from Singapore. He headed our team, and our team finally could make it, and it was very successful, as you can know about it. The total span of this bridge is 100 meters, and it has been supported at a 100-meter level. There are 4 level decks. I have repeated this time. The number of joints, as you can see, the statistics are there. A number of bolts, the thickness of plates. See, it's 10 mm to 150 mm. Grade of steel is E350. We could have, these days, I think, more than this is available in the market, but not in India. At that time when he conceived, E350 was the steel that was available in the international market. And the self-weight of the steel structure itself was 2340 metric ton, which is quite a considerable amount. Now, the structure, as we conceived it, as you can see, as a beam-like structure, and which has a catenary to it, so that the serviceability and the deflection of the whole thing can be, it can be managed to the limiting values we have. Now, the system that if you can understand that the entire bottom part, that's the bridge part, that is the main spine of the whole thing, spine of the entire bridge. And you have a crown to your left, and you have the top hat at the center, and again to your right you have the crown. So the bottom part, that the bridge part, the blue part, which you can see, it's taken from our computer model, is the main support system to the entire thing, and the crown and the top hat. Top hat is adding some stability more towards the deflection of helping us towards the deflection serviceability of the thing. But as a strength, the bottom part is giving you the strength so that the entire load is coming onto this thing. So this is the anatomy of the Dea that the components are. There's a longitudinal truss, there's a transverse truss, a floor dia grid, horizontal arches, well trusses, vertical arches, roof arches, crown, and the external dia grid. Now, if you can see that we have just tried to take out some of the major components of the whole bridge. The first one, that the longitudinal truss is or the truss girder, is basically supporting the entire structure longitudinally. And from there, we have this transverse trusses which are longitudinally, which are transversely attached to the longitudinal truss and cantilevering out. There's a floor diagrid which is providing a lateral bracing to the whole system, as well as the floor systems are supported on this lateral bracing. We have horizontal arches on the sides to take care of the wind forces and take back again to your longitudinal truss. You have noticed in the beginning that there is a well as a hole at the center. It was intentionally kept not to reduce really the wind load, but it was architect's dream to have a hole in your hole at the center. So this well truss is supporting that well at the center, and the vertical arches are the structure which enhances, as I said, which is helping us in reducing the deflection of the whole structure. Then we have the roof arches and the crown and the external diagrid, which is, this external diagrid is interesting. You know, we have finally put an external diagrid so that it is also helping in supporting the facade, as well as the entire structure. It takes as a whole, it gives a much more rigidity to the whole thing. It acts as a more solid shell-like structure rather than a single unit. Now, while understanding the model, we did the computer analysis. It was okay, fine with the serviceability. Then we came into how to fabricate, how to understand the joints, how to approach the joints, and then how to erect the whole thing. You can see on the left that is again the anatomy, and it is a perfect real-life model that we have done to your right, to understand the joints, to approach the joints. How do we approach the joints to connect, for the connections, for the weldings, etc., etc. There were difficulties. We could estimate that there were difficulties, and you can see at the bottom of the picture that the king truss, the main truss, has been erected. Well, here I would like to thank the contractor, which is an international contractor, Eversandai, who did the whole fabrication erection, and they helped us just like anything. And there was a gentleman called Sarvanan. I must tell you that he is a genius. He helped us out to solve many of the problems, which, see, this is a kind of thing that in everybody's life, this is the first time, probably the last time. So we didn't anticipate many of the problems which would come in the beginning. And eventually, when we did the design, when we tried to understand the execution, the erection, we came across many of the problems which we had to sort it out instantly. So the design criteria that we primarily fixed up is of course, the stability check of the bridge for the vertical and the lateral stability, and the check for the stability check for the building with respect to the forces that generated due to the bridge. For example, what the building is standing from, and the bridge is, as you can understand, it's a tall structure there with 4 level decks and 100 meters long. The surface area and the wind that will come, that will affect your building structure itself. So that was one of the criteria how to solve it, because it was, the forces is astronomically high at that. We did the for the wind tunnel test also in Singapore. Then the major thing that we were struggling, how to support the whole system, what will be the support conditions. As I explained earlier, that there can be interfaces between in movements of the buildings. The building is moving this way, the other can, in seismic conditions, the other can move the other direction, and there can be phase lag in the dynamics of the whole building. So this movement will definitely generate a twisting in the whole bridge and the turning in the whole bridge. So initially we thought of doing a pin connection between the two buildings. But the forces that were generated from the breach, the lateral forces that were generated from the breach to the building, we couldn't support the building with in the serviceability conditions, because the sway of the building has to also be catering to the comfortability of the people staying there. So there is a acceleration that will generate in the building, which we have to take care. Then we thought of releasing the forces. Second thought was pin-1-1 connection and the roller on the other side. Then again, we realized that yes, the bridge is released, the bridge is out of stress, but again, the building is not safe. The left building is attracting all the forces together. So that is also not done. Then came that, well, we cannot sustain this type of support system. Then we came across the spring system, the spring support system, which will allow the building to move in its own plane. So the release of the forces will happen, and probably this is the thought of base isolation that emerged out. At that point of time, well, base isolation was, yes, we heard of that, but what it is really, we were not aware of them, we were not familiar with, rather, with base isolation. So then we got hold of one of the major designer, R.J. Watson of US, to help us out in designing the bearing. Then they came across with a very nice design, and they found out this erratic wake bearing. Now this erratic wake bearing is you know, it's a bearing. If everybody is aware of the you know, the upholstery of your car. If you have anybody seen the old Ambassador cars, there are vertical springs and there are horizontal springs in all directions. What it is doing really? It is just giving you the comfort when the braking, when it's accelerating, you are not moving. So because this seat is adjusting, the spring is adjusting along with the movement. So the similar kind of thing has been adopted there, and I think gradually we've found that yes, this is the answer to the whole support system. This is the base isolation, the concept that if you can see to your right that this is the actual bearing that has been placed underneath the girder, and this is the technical drawing of the bearing. And the bearing, one such bearing, we used 4 such bearings, and each one of the bearing was weighing, the self-weight of the bearing was about 15 tons. It was, again, a nightmare to lift that 15 tons up there at the 100 meters level. It was, again, and then again, we never thought of that suppose at one point of time, it's this bearing needs to be replaced. And so we did some rails underneath so that it can be taken out and then replaced, jacked up, and then, so I think Our Lady has given me a warning of 2 minutes, I don't know. So the fabrication and erection, it has been talked throughout the country with the fabrication and erection. But again, let me tell you that the end segment were erected on site, and this mid segment were lifted through jacks and strands up there and fitted. And one of the such joint you can see to your right corner, there is a joint which is a typical joint that was fabricated and taken up to the side. There's to your right, you can see one of a typical joint. How many protrusions that has come out from one joint. So this is again the connection of the beams and the infills. So this is the erection that has happened. You could see to the number 2, the middle part lifted and attached to the end base. And this is the final pictures of the the first one to your left is, we didn't have any bridges there. And then to your right is the end segment has been fabricated. The bearings are lifted, bearing placed, and the central bay has been there, and the right two pictures are the current day picture right now. It has been executed right now. This is how the bridge looks today. It's in our city, so anybody going there, and it's at the heart of the city, I know that many of you have seen, but even if you haven't seen, I think it's worth seeing. It's our city's pride. It should be our city's pride, and we would hope we engineers have made you proud of our city, and many such things will make it. Don't worry. Do you have time for some one of? Okay. Another very interesting project, which is to my heart. We did it's a commercial buildings mindscape in Faridabad. This is two buildings again, 3 basement plus ground plus 9, and the other one is 3 basement plus ground plus 13. And we have a 30-meter bridge. This bridge is not a bridge; it's an office space. And again, the same concept of connection of the two buildings was a problem, and it was. See, if you can see that we have 4 levels of bridge, and again, the concept was base isolation. We did the base isolation, but in a very, very smaller scale. Of course, not in the scale of atmosphere, the heavy load that we have taken there. And the bearings were also much lesser in its capacity than the atmosphere. The plan looked like this, with the bracing, central bracing, and girders are closely spaced girders. Well, I think it's time, right? So thank you. I think